Okay, good afternoon, everybody. So this is Mass 465 class, and then 1, 3, and 1, 4. Two sections are due this Friday. Do you have any question about the homework on 1, 3, and 1, 4?
I have a question on
Yeah.
for exercise 1.3, number 13. I was wondering if you can go over C.
Okay, 1, 3, number 19.
No, number 13.
13, okay. 13, okay.
Thank you.
All right, let's do 2 dice roll an outcome. Outcome is a sum of the points. So on the first row, the sum is 7 or 11. Then the person wins. And then the first row, the sum is 2, 3, or 12, then loses. And 4, 5, 6, 8, 9, 10, then a point. Okay, on the second row, in the second row and on, when the point is established, then rows 7 before the point, then loses, and then a point before 7, then wins. Okay, very complicated. Let's try. Number 13. This is 1, 3, 13. Okay. Number 1, 3, 13. And then first question is the sample space is what? Okay, let's see the sample space. What is the sample space? 2 dice a roll. Okay, 2 dice a roll. So we have die 1 has number I, and then die 2 has number J. Okay, this is a possible one. Okay, I, J, this pair. So I and J are from 1 to 6, right? This is a sample space. Oh, there are 36 outcomes, right? And then part B is what is probability that the sum is 7 or 11? 7 or 11. It's like convenience store, 7 and 11. Okay. What is a probability? How to get this probability? So that means I plus J is either 7 or 11, right? I plus J is I plus J is 7. Okay. Which kind of pairs are there? I and J are 7. So that's gonna be if I is 1, then J must be 6. If I is 2, then J must be 5, and so on. Okay. And then 3 and 4, right? And then last one is 6 and 1, probably. How many? 1, 2, 6. So 6 cases, right? 6 cases. I plus J is 11. Then what are the possible ones? 11. 1, 2, 3, 4, 5. Okay, 5 and 6, right? And then 6 and 5. That's it. Only two cases. Okay? Two cases. Only two cases. And then sample space has 36 points. Okay, this is 36. 36 points. And then out of 36, 6 points are here, or 2 points are here. So total of 8. So this probability must be 8 over 36. Make sense? Well, you can simplify it as 2 nines, 2 over 9. Okay. I think this is okay. Don't write 2.22222. No. Okay, 2 over 9 is fine. Part C is let me read the question. This is 1, 3, 13. 1, 3, 13. But we find given that 8 is the outcome on the first row, find the probability that the beta now rolls the point 8 before rolling the 7 and then thus wins. Note that at this stage in the game, the only outcomes of interest are 7 and 8. Thus, find the probability that conditional probability of 8 conditioned by 7 or 8. That's what we have to find. So part C is a probability that 8 is coming based on the condition that a 7 or 8, right? This is the one. This conditional probability. Well, this is equal to what? This is by the definition of the conditional probability, P of 8 divided by P of 7 or 8, right? 7 or 8 contains 8. So 8 and 7 or 8 is just 8. Okay, this is the one. Can you get this probability? 8 comes. Okay? 8 comes. Sum is 8. Sum is 8 means the thing is you have to start 2, 8. And then 3, 7. Okay, up to, I don't know. What? Wow, I'm crazy. I'm sorry. 8, yeah, 2, 6. I'm sorry, 2, 6, 2, 6, and 3, 5, and then 4, 4, 4, 4, and then 5, 3, and then this is 3. Okay, and then 6, 2. Okay, how many? 1, 2, 3, 4, 5. 5 possibilities. Okay, 5 possibilities. This probability is 5 divided by 36. Okay, and then this probability 7 or 8. 7, there are 6 cases. 8, then 5. So 6 plus 5 is 11. Okay? 11 over 36. Okay, so that's the answer. Okay. What about part B? Part B is the probability that the beta rolls an 8 on the first row and then wins is given by P of 8 times P of 8 conditioned by 7 or 8. So show that this probability is 5 over 36 times 5 over 11. Yeah, we can do it. That's easy. So part D is P of 8 times P of 8, 7 or 8, right? P of 8, we have seen P of 8 is 1, 2, 3, 4, 5. Okay, 5 possibilities out of 36. So this P of 8 is 5 over 36. And then we figured out this guy. Okay, this guy is a 5 over 11, right? So we're done. Okay. And then E is win probability of win. How do we win? And there are several cases. Okay. First case is what? 7 or 11. Okay, 7 or 11. Okay. First one is 7. Get the probabilities of 7 or 11. Okay, this is the first case, and then plus other cases. Other cases are what is the other cases? 2, 3, no, 4, 5, 6, 8, 9, and 10, and then point that is given, and then a point before 7. That's the case. So I did for 8 and then 7, 6. Yeah, okay. Other cases. First one is 8, and then second one is 7 or 8. Yes, we should get use a part P. So this is P of 7, 8, and then times the P of 8 conditioned by 7 or 8. Okay, this is the case, and then and also this is 1, 6, 8 is replaced by 6. I guess this is replaced by 6. This is replaced by 6. And then we have the same probability, So 2 times of this will come. 8 and then 8 and 8 can be replaced by 6. And then we have 2 times of this guy. Okay, and then 2 times of the same thing for the 4, 5, and 9, 10. Okay, 4, 5, and 9, 10. That is a P of 8. Next one is a 9, and then P of 9, and then 7 or 9. Okay, and then this 9 is replaced by also by 5. Okay, 5. This is replaced by 5. Okay. And finally, we have 2 times the probability of 10, and then probability of 10, and then 7 or 10. Okay, and this 10 is replaced by 4. Okay? 4 and 4 also. So we have 2. So this is 1, and then calculate this guy. That's the answer. I'm talking about the point case. 4, 5, 6, 8, 9, and 10. We have point. And then to win that one, we don't have, we like to have those numbers before 7. So that's the one. That's the case. So the process is given by this and this. In this case, we're dealing with 8. Okay? 8. And replacing 8 by 6, or 9, or 10, or 6, 5, or 4. Okay? That's the idea. So this is the probability of winning. And please calculate this one. Okay. Any other question? Oh, this part is of course a 5/11. Yeah, 5/11. Very good. Do you have any question about 1, 4? Okay, if not, then I shall proceed. We are doing section or chapter 2, and then section 2 on random variables of the discrete type. And then I define the random variable. So that's what I did last time. So, okay, proceed. Okay. When chapter 2 and section 2.1, that is random variables of the discrete type. random variable. Random variables of the discrete type. And then I defined the random variable last time, if you remember. So this is a review for you and for myself too. Okay, first sample space is there, okay? A sample space. And then the random variable is a function on sample space S. Okay? X is a function defined on sample space S. And then usually taking a real values, taking a real value. And this is called a random variable, random. Random variable is a function defined on sample space. Then what is the difference between the usual function and then a random variable? We're talking about discrete case, discrete case. So usually this is consisting of a finite many points. Well, it could be infinite, like S1, S2, S3, and so on. It could be infinite. Could be stop at the finite many points. So if S1 is given, then X of S1 is defined, and that is giving you some real number. X of S2 is some real number, of course. But the point is that we don't know if you do an experiment and then one of the outcomes will come, but we don't know S1 comes or S2 comes, S3 comes, we don't know. But we know the probability of S1 happening or S2 happening. So probability is involved in random variable. That's a difference. As X of S1, yeah, X of S1 is some number, of course, X of S1. This is a real number. This is when this is given. But we don't know this happens, or next one happens, or next one happens. We don't know. So there is a probability involved. Okay? That's the difference between the usual function and the random variable. Random variable has uncertainty and the probability is involved. Okay? That's the difference. So let's see an example, then you will see more, okay, more clearly. I'm going to use the text example 2 and 2. So this example. Roll a six-sided die. Roll a six-sided die. And so necessarily the sample space is consisting of 6 numbers, 1, 2, 3, 4, 5, 6. This is a sample space. Oh, by the way, I'm sorry, I forgot. Okay. This is a random variable, and then notation. This part is confusing, so I'm going to use this of x, space for, okay, space for x, space of x. This is a set of all x. And then x is equal to s of x, s of s, x of s. And s is varying on the sample space, okay? This is a definition of s of x. Very confusing. S is a sample space. And this is a space of x. Namely space of x. There's the space of x. Space of x. Very confusing. And simply this is a range of x. Range. Function x is range. Okay. So we can consider this way. I'm gonna use a subscript here, s sub x. So indicating that this is a space of x. If I don't write this x, then it's gonna be same as this x. sample space. It's confusing. Okay, so these x, S1, S2 need not be a number. It need not be a number. But this value, this is definitely a real number. Real number. It's a number. But these may not be numbers like men, women, whatever. Okay, so sample space need not be a number. Like when you use two die, then you have a pair of numbers, I and j. Okay, that's not a number. That's a point in two-dimensional space. So very confusing. Sample space is not necessarily consisting of real numbers, but some other stuff. Okay. But value of a random variable is always a real number. Okay. So this is a subset of R. Space of X is a subset of R. Okay. Range of the random variable X. So here's an example we're talking about. Roll a die, six-sided die. So S is a sample space, 1, 2, 3, 4, 5, 6. Those are the outcomes. And then XS is a random variable is defined. X of S is defined to be S. What? Okay, yeah, this is the one because S is consisting of real numbers, so we can have this function. S is mapped to the number S itself. Okay, so necessary the space of X, the space of X is denoted by X sub S sub X, and then this is same as the sample space is. Okay, don't be confused. Space of X is a range of X, and that is happen to be the same thing as the sample space. This is a sample space number, right? But this is at the same time a real number. This happens. Then what is the probability that X is equal to S? What is this guy? The random variable takes the value S. What is this probability? S happens. This probability what? Assuming that we're using a pair die, then this happens with the probability 1/6, right? One appears with the probability 1/6. 2 appears with the probability 1/6, and so on. Everything is appearing with the probability 1/6. So this is a probability. Okay? S is in S. So these are the given thing. Okay, so we are using a pair die. Okay, then tell me the following. What is the probability that X is equal to 5? X is equal to 5. That means number 5 appears on the die. Then this probability is, of course, 1/6. Okay, 1/6. 0.16666. Next one. What is the probability that X is between 2 and 5 inclusive? What is this probability? This is same as saying X is taking the values 2, 3, 4, and 5. Okay, 2, 3, 4, or 5. Now 4 numbers. Each one has the probability 1/6. So we can add those guys. Okay, 1/6 plus 1/6 plus 1/6 plus 1/6. It will be 4/6. Okay. Of course, you can simplify this as 2/3, 0.66666. Well, finally, what is the probability that X is smaller than or equal to 2? Smaller than or equal to 2. This is the probability that X is equal to, X can take 1, 2, 3, 4, 5, 6. So X is 1 or 2, right? So 2 choices. So this is 2/6 or 1/3. Okay. That's a probability. I can tell this way. In this case, the space of X is happen to be the same as the sample space. This happens sometimes. Okay. But remember, space of X is the range of X, and we're going to use the notation S sub X in this X. If we write S, then it's very confusing. That part is a little bit bad about this textbook. The authors are very good. Very good means that they are fine researchers, and then they're making very nice textbook. Okay, so this is a example. We need more terminologies. Okay, terminologies. Right. We like to get the probability mass function, probability of mass function, PMF, probability mass function. So setting is X is a random variable. I'm going to abbreviate this as R dot V. Okay, R dot V. This is indicating a random variable. You don't have to write random variable, but R dot V that indicates the random variable. And then I'm going to use S sub X. In the textbook, S is used. This is a space of X, a space of X. This is a range of the function X, range. And then for any subset of S sub X, we can attach a probability. So probability of X is in the subset A of S sub X. This is given. This is given. For any A that is a subset of the space of X. Any subset of S sub X, we can consider the probability that X belongs to A. X belongs to A means that X of S is going to be in the set A. Okay, that's the meaning of this. So these three things are given. Okay. Random variable is given. Random variable is a function. Okay, X is a function from S to R. Okay. This S is a sample space again. Sample space is a set of all outcomes of an experiment, maybe. A sample space is S. And then this S sub X is a space of X that is a range of X, as we have observed, range of X. And we can attach a probability for any subset A of the space of X. Any subset, we can consider this probability. X is falling into the subset A. And this probability can be given. Then we say that the distribution of probability associated with the space S sub X of X is identified. Okay, so these guys, X of A and then A is a subset of S. Okay, this is called the distribution of probability. Distribution. The distribution of probability. Distribution of a probability associated with the space S sub X. Okay, this is the terminology. This is called the distribution of probability associated with the space S sub x. And then the simple case is this need not contain 2 or more points, but only 1 point is fine. If A is consisting of only 1 point, then that's very simple. And then that's going to be the one we like to consider. And then this is called the probability mass function, a special case of this. In this case, we are not saying the random variable is discrete or continuous, so we're not saying anything about this. But the discrete case, we can have the probability mass function. And this A can consist of only 1 point, okay? We say that's a point. So discrete random variable has the probability mass function, and then probability mass function is the probability that x is equal to some particular number, So let's see. Okay. The next step is we're given a random variable again. Okay. Random variable, okay, and then the time, okay, about 40 minutes, okay, good. And then S sub x, this is a subset of real numbers, the space of x. Again, okay, space of x. And then S sub x is consisting of countable number of points. So that means we have S sub x as x1, x2, ... Could be infinity. Okay? So a countable set, countable, or finite, okay? More finite. Finite set. Finite set, yeah, you see the meaning. Countable set is we can count x1, x2, x3, x4, and then going forever. But no more than that. Countable means we can count. The first one is this, second one is this, and third one is this, and then we can proceed this process, and then everything is gone. Okay? That's possible. That is countable. More than countable is continuum. Okay? Continuum means just like interval from 0 to 1. 0-1 interval contains infinity many points, but it's not countable. We can't pick first one, second one, and then continuing that process, and then everything is moved out. No, that's not possible. So more than countable set is like 0-1 interval. Well, the real number line itself, okay, that has, well, this one has more than countable number. Did you know this kind of concept? Uncountable, countable? Maybe you have heard this one. Countable means that we can count anyway. First one is this, second one is this, and we can count. But uncountable means we can't count. Just infinitely many. Okay, more than countable. That's an uncountable set. Anyway, this is the idea. Okay? Kind of we have a sequence, and then this is the infinite sequence. We can think that way. And then if this is the case, the only thing is that it's a countable or finite set, and that's the assumption. In this case, we have x is a random variable of the discrete type. We say that x is a random variable of the discrete type, This is our terminology, okay? Discrete type. Other than discrete type, we have a continuous type. Continuous type means the values are taken kind of continuously, okay? Not countably many, but more than countable. That's the discrete type. And then, or we say x has a distribution of the discrete type, or you can say x has distribution of the discrete type, This is the definition, okay, of the discrete type again. We say X is a random variable of the discrete type, or we say X has the distribution of the discrete type. That's all. And then important thing is that in this case, we can have the probability mass function. Probability mass function. That is, this is really a function, okay, f of x. X is a real number, and then this is indicating the probability that x is taking the value x. So this is obtained for any x, real number x, and then we can consider this probability, and then this probability depends on x, so we can write f of x. And then first of all, we consider x is in the space of x. Then we have some positive number. Other than this set, in this set, then probability would be 0, as you can see. So this function is called the probability mass function. Probability mass function. Function is ft dot. Probability mass function. Ft dot means function's abbreviation. Okay? Function. You don't want to write function, right? I don't want to either. So ft dot indicates a function. And sometimes this is abbreviated as PMF. Okay? PMF. This is abbreviation. We're going to use this PMF, probability mass function, later on. So this is a definition of the probability mass function. And actually, I gave the definition, but here's an official definition, probability mass function. Well, properties of the probability mass function. So we should see the properties of this PMF. Then I will see better. So let's see. Here's a definition. Definition together with the properties of PMF. So f of x is the PMF, the probability mass function of a discrete random variable of a discrete random variable x. And then space of x is denoted as S sub x. And this is, of course, a subset of R. The textbook is not using this S sub x, just S, but it's confusing, so I'm writing sub x, okay? And then this is a PMF of discrete random variable. So PMF, this is the definition, PMF. When in this case. This is a definition, okay? Definition is f of x is a function. F of x is a function. Function such that. So of course f is a function from where to where? What do you think? The space of x to real numbers. Okay? But you can consider this is indicating a probability here. So probability is between 0 and 1, right? So f is a function from S sub x to, we can restrict to 0 to 1. That's okay. Because this probability is always between 0 and 1. So you can write 0 and 1 here. That's okay. So three things. F of x, this probability is positive, okay, positive, true for any x in the S sub x. And so necessarily we can say that this set is a support of the function f. Support is denoted as SUPP, support of f. Okay, we can say. Support is by definition the set of a subset of a domain for which each point has the value of f positive. That's the definition of the support. That means outside of the S of x, the f's value is 0. That's one. So outside of S of x, the value of f is 0. Not negative, but 0. Okay. And then since this is a probability mass function, what about the sum of all these guys? The sum of all these guys, possible x. Then that should be equal to the entire space. So that should be 1. Since we have the property that we add f of x for all x that is in S of x, the range of x, and then this should be equal to 1. Okay. That's the second property. And then lastly, as we go back here, this A is a subset of S of x. How do you calculate this one? Okay, that's a point. So we can calculate that one by the sum, P that x is in A. This probability is calculated as we collect all the f of x value. And then this x is in A instead of S of x in A. This is a property. So A is a subset of S of x. Okay. Well, these three are the properties that should be satisfied by the probability mass function. So one more time, the probability mass function is defined on the space of x or range of x into the set of real numbers. Well, you can restrict to 0 to 1, the one interval, and a positive on the set S of x. So necessarily we can say S of x is a support of f. And then we collect all the probabilities, P of x is equal to x. And that sum should be equal to 1. Okay. And then for any subset A of the space of x, then we can calculate this probability x is going to be in S. This probability is calculated by summing f of x for x is in A. In this way, we can calculate the probability. So that's the definition of the probability mass function. Okay. So two more things. Probability mass function is defined, and we like to define a cumulative distribution function. So this is defined for any random variable, not necessarily discrete. So here's a definition. So x is equal to x is from the sample space to R. Okay, this is a sample space. Yeah, don't be confused. This is a random variable. Okay? Yeah, I should mention S is a sample space. And then we define capital F of x. Then a probability that this is a real value, so this function is taking a smaller value than or equal to x. Okay? This is considered. For any x real number, the probability that the random variable x is taking a smaller than or equal to x value, okay? This probability can be considered. This is considered. Then this x is any real number. Okay? And then this is a function of x. Okay? This is a function of x. The probability that x is taking a value smaller than or equal to x, This probability is a function f's value at x. So this is called the cumulative distribution function. This is a function of x, so this is a cumulative distribution function. Okay. Cumulative distribution function. That's the name of this cumulative distribution function. So we abbreviate this as CDF. Okay, CDF. Cumulative distribution function. PMF is a probability mass function. Okay. One more thing will appear for the continuous random variable probability density function. So PDF. It's like a PDF file, but PDF, probability density function. PDF, PMF, and CDF. Okay, those are the ones we're going to use later. PMF for probability mass function, CDF for the cumulative distribution function. So I want you to get used to, okay? So that's one. So necessary, okay, this probability, this is a probability. So this number is between 0 and 1. So we can say necessary. The property is f of x is between x 0 and 1. Okay, this is true for any x. Is that right? What is the value at negative infinity? What do you think? Also, what is the value at infinity? Of course, these are not real numbers, but this is the idea. If when x goes to negative infinity, then what is the limit? That's what I'm asking. What do you think? Negative infinity, then there's no number less than or equal to negative infinity. So this probability should be 0, right? This probability should be 0. Because there's no number less than negative infinity, less than or equal to negative infinity. What about this? This is replaced by infinity. The value of x is, of course, always less than or equal to infinity here. So this happens always. This happens always means the probability of it is 1. Okay? Reasonable? So the function value is between 0 and 1. Okay? In negative infinity, it's going to be 0. Infinity should be 1. Okay? So these are the properties of the cumulative distribution function. And there's one more property. Because of this equality, the function is continuous from the right. Okay? From the left, we don't know, but from the right, it is continuous. So we'll see. So this is a property of the cumulative distribution function. Okay. So we have defined the probability mass function here. Okay? Probability mass function here, and then these are the properties. Okay. And then also we can define the cumulative distribution function. One thing we have to note. Okay. We're not assuming this is discrete. This is discrete. Any random variable is fine, not necessarily discrete. So cumulative distribution function can be defined for any random variable, discrete or continuous, whatever. We'll see. Anyway. Now, special case of the cumulative distribution function, we'd like to see an example. That is a uniform distribution. Okay? Uniform distribution. So we have defined a cumulative distribution function. And then one example is uniform distribution. So let's see. Okay, let's see. X is defined on the sample space S, and then to the range of x. This is s sub x, and this is happen to be consisting of finitely many numbers like 1, 2, up to m. Okay. The space of x is consisting of m numbers, 1, 2, 3, 4, 5, up to m. Good example is rolling a die. Rolling a die, then a sample space is 1, 2, 3, 4, 5, 6, and then the number on top of the die is 1, 2, 3, 4, 5, 6. So that's the same thing. So in this case, m is equal to 6. Okay, that's the case. Consider that case. This is a discrete random variable. Okay, discrete random variable. Discrete random variable. So s sub x is 1, 2, up to m. Now, in this case, we say the distribution is uniform. Distribution is uniform. Distribution is uniform when then each one will appear with the same probability. That's the case. So here's the definition. Each outcome, okay, outcome means that this value is 1 to up to n will appear with the same probability. So that's gonna be f of x. Remember this, the PMF, probability mass function. This is by definition x is equal to m. X is equal to x. And this is equal to, what is the equal probability? M object will appear with the same probability. So each one's probability must be 1 over m, right? 1 over m. Yeah, somebody is trying to say this. Thank you. So x is in s sub x. Each x will appear with this probability 1 over m. This is a probability mass function, okay? The probability mass function of x. PMF of x. This is the one. That's the definition. Then I'll ask you, what is a cumulative distribution function then? Can you get the cumulative distribution function? And then note that this is a domain on a range of the random variable x, but this x can be any real number. Okay? That should be considered. Any real number. So we have this kind of thing. When this x is negative was less than 1, what happens? If this x is smaller than 1, what happens? If this x is smaller than 1, then x can be equal to this x smaller than 1. This doesn't happen, right? So that probability is 0. Is this okay? Right. If x is smaller than 1, then this x can't be equal to that number because at least 1, okay? And then at most m. So less than 1, then there's no way. So that probability is 0. Okay. So yeah, let's see. This is defined by the formula x is smaller than y equal to x. This probability is f of x. It's a cumulative distribution function. When this x is smaller than 1, then x can't be equal to that number, right? At least 1. So this probability is 0. Make sense? What happens if the value is greater than or equal to m? When x is greater than or equal to m, okay, this number is greater than or equal to m. And what is this probability? This x is taking a value is 1 to up to m, and this number is greater than or equal to m. So necessarily x is more than this x happens all the time. For instance, this is m plus 1. then this inequality is true all the time, right? That means this probability is 1. Okay, 1. If m is smaller than or equal to x, or x is greater than or equal to m, then this probability is 1 all the time. Okay, that's 1. And then we have to think about between 1 and m. Okay, I want to show you k, and then less than or equal to x, and then less than k plus 1. Okay, k plus 1. And then k is equal to 1, 2. Okay, up to m. Okay. So consider cases. X is between k and k plus 1. Then what is this probability? Can you get this probability? All right. Then let's consider, for instance, okay, f of say 2.5. Okay, 2.5. This is x is less than or equal to 2.5. Okay, this is 1. X is f of 2.5. F of 2.5. That means probability that x is smaller than or equal to 2.5. But x cannot take 2.5. But with this restriction, x can take which values? What do you think? X can take 1, 2 up to m. Then x can take which number? Can take 1, can take 2, but not 3 or more. Only these two guys, right? Then what is this probability? X is taking only 1 or 2, so 2 possible values. And x is equal to 1 is 1 over m. X is equal to 2 is also 1 over m. So this probability must be 2 over m, right? 2 over m. Do you agree? Please agree. Then necessary, okay? X is between k and then k plus 1. K is an integer. Okay? Then f of x, and then x is between k and then k plus 1. Okay? This is p, x is smaller than or equal to x. Then what do you think? The x can take which kind of value if this is the case? X is greater than k, but smaller than k plus 1. The x can take 1, 2, up to what? K is possible? This k is possible? Yeah, because x is greater than or equal to k. K is possible. But what about a k plus 1? Is that possible? No, because x is smaller than k plus 1. Well, this is a 1. Okay, this is 1. X can take the values 1, 2, up to k. Then what is this probability? There are k values out of m. So k over m, right? So this value is k over m. Okay, this is a cumulative distribution function's value. So we have to classify. Okay? We have to consider these cases. 3 cases. Looks like 3, but this case we have n cases over here. But it's okay. Okay. Gather in one case. So this is a cumulative distribution function of this uniform distribution. Okay. Uniform distribution case. Uniform distribution case. The probability mass function is constant for any x, constant. Always same number. In this case, we can get the probability cumulative distribution function as this: 0 up to 1, and then some number between k and k plus 1, and then after m, it is always 1. Okay, this is a function. And then I need to draw a picture, draw a graph of this function. Okay. If you see the graph, then it's very interesting, and then you can see better. Okay, so let's see. And this is a 1. Okay, and then can you do a picture of this guy? Graph. 1, 2, 3, 4. Say this is M. This is M. This is 1. This is 2, and so on. 0. And as you notice that the 0 is the value, minimum value, and 1 is the maximum value. So 1 is somewhere here. Okay? 1 is somewhere here. And then go up. Okay. So the graph of the cumulative distribution function is always between the lines. This is y is equal to 0, and this is y is equal to 1. Okay. All the time, the graph of the cumulative distribution function is between the line y is equal to 0 and then y is equal to 1, okay, between those two. So right here in a strip, the graph exists. And then this says up to 1, okay, up to 1, it is 0. So this is open dot, okay, and then the body is like this. Up to 1. 1 is not included, but it is 0. Okay, so this is the first part. Less than 1, then it's going to be 0. Okay, 0 over here. And then we have, say, some number. I don't show you a lot, okay? This is the next step. Next step is 1 to 2. 1 to 2 is a k over m, okay? 1 over m. So 1 over m is here. This is a closed dot, and then go like this, and this is the open dot. The next step, we have a closed dot here, and then open. Okay? Yeah. Oh my gosh. Next step. So m is m minus 1. This should be m. This is m plus 1. Okay, that's the idea. M minus 1, it is here. What? Am I wrong? Yeah, I'm wrong. I know. This is the one. And then next step is this one. So this is m plus 1. This is m plus 2. Okay. So this is m minus 1. The graph goes like this. After m, it is 1. Before, we have a kind of step function like this. And right hand point is an open dot, and then left hand point is a closed dot. Okay, that's the idea. And so this is a graph of the cumulative distribution function. Okay, 1, 2. This is just one example. 1, 2, and then up to m. M is here. So we have to, if you want to have this guy, then I have to split this interval into more subintervals. Okay. So this is the one. So anyway, the graph of the cumulative distribution function is always between y is equal to 0 and then y is equal to 1. And also, you can see that the function is increasing, not decreasing, nowhere decreasing, but increasing. And in this case, go to the right, go to the left. Okay, from the right side, this is a closed dot. This is indicating that the function is continuous from the right side. Continuous from the right side, right side, right side. That's the property. Because of the definition of this, equality sign is over here, so the function is continuous from the right side. Okay, so this is a picture of cumulative distribution function. For continuous type, things like this continuous and going like this, we're going to see this type of function, cumulative distribution function. Discrete, and then uniforms are going to be 0 up to this point, and then that. It's an increasing kind of step function. Stair. Okay? So that's the one. Okay, we have 6-7 minutes. All right. I don't go fast, so I don't want to go fast. So anyway, this is a graph of cumulative distribution function. And then one more thing I have to do: a graph of probability mass function. Okay? Probability mass function. So this is a graph of cumulative distribution function. So now I like to get the graphs of f of x. Okay. This is a mass function, probability mass function given by 2x minus 1 divided by 16. And then x is equal to 1, 2, 3, 4. Only for 1, 2, 3, 4. But the probabilities are different. When x is equal to 1, then this f of 1 is 1 over 16, as you can see. X is equal to, then 4 minus 1 is 3. It's 3 over 16. 3, then 5 over 16. 4, then 7 over 16. Okay, those are the values of probability mass function. And then I'm saying graphs of this. There's only one function, but why graphs? And there are two types of graphs. One is a bar graph, and then other one is a probability histogram. So we'd like to show you two distinct ones. So a bar graph looks like this way. Bar graph. And then 1, 2, 3, 4 will come here. 1, 2, 3, 4. 1, 2, 3, 4. This is x. Okay, so this is 1, 2, 3, 4. And then the values are 4, then it's going to be 0.7. So we have 1, 2, 3, 4, 5, 6, 7. Okay, this is 0.7. No, not 0.7. Some other number. Okay. This is 1/16th. Okay, this is 1/16th. The first one is 1/16th, and so on. Okay, and then this is 7 over 16. Okay, this is 7 over 16. 1/16th, 7 over 16. And a bar graph. So first one is this. Okay? This is the graph from here to here, 0 to this. Second one is 2. So 2 over, I don't think so, 3 over, and so 3. So it should be somewhere here. This is the graph. First one is this high. 3, it's going to be 5. Okay, 5. So we have a bar from here to here. Okay, this is a bar graph. And the 4, it's going to be 7 over 16. So we have a bar graph like this. These are the ones, bar graph. This one, and this one, and this one, and this one. These are the bar graph. Bar graph. Bar graph. Next one is the probability histogram. Essentially same as the bar graph. The thing is connected to next to each other. And then we have x, and then 1, 2, 3, 4, 3, 4, 1, 2, 3, 4, same as before. And then we have kind of a rectangle, okay, rectangle. So first one is this, second one is this, third one is this, and fourth one is this. This is a histogram, okay? This is 7 over 16. The first one is the 1 over 16. And called the probability histogram. Okay? Probability histogram. And so these two things. Probably homework questions. The questions are asking draw a bar graph and then probability histogram. Okay, so they are asking you to draw bar graph and then a probability histogram. So these are the ones. These are the ones. I want you to get used to these guys. Okay. All right, this is it. Do you have questions?